Okay, let's get going. So we were talking about Mobius transformations. Which are mappings of the kind like this. And what I was in the middle of showing you was that Mobius transforms map lines to circles or lines. Okay, and we showed that M can be thought of or can be written as M of Z is equal to L2 L1 of Z, where L1 and L2 are affine mappings. Right, i.e. affine. I want to write specifically what L is because it's a specific form. Affine means we have Z goes to, say, AZ plus B, right? That's an affine mapping. So the fact that affine mappings send lines to lines, circles to circles is trivial. So the real thing that has to be checked is that this thing, the inversion mapping, actually does that. Okay. So Mobius transform transforms space with an affine mapping, then it inverts it, then it transfers it back. Cool. Okay. So we were somewhat into this. Let me call some part of this. I think we showed was that if we have a circle that goes through 0, then that is mapped to a line. So first, let's observe how we can write a line in the complex plane, or the equation of a line. So look at this. So if we have Z like this, then typically we write a line something like this. Say AX B is equal to C. That's how we'd write a line, right? That's the equation of a line, yeah? That's a line which goes orthogonal to the vector A comma B, right? And the C here dictates where in space it actually is. If C was 0, then it would be the line orthogonal to AB going through 0, yeah? You're all happy with that, right? Yeah, thumbs up if you are, yeah? Cool, all right, so if we wanted to write this in complex coordinates, well, what do we know? We know that we can write X like this. So we can write this as Z plus Z bar over 2, and then B as the Y. We can write this as Z minus Z bar over 2I and C, right? Because if we do that, then we kill the X, and yeah. So this is another way to write this thing like this. And then if we solve for Z and Z bar, then we get the following equation. We're going to have that Z over 2, and we're going to have an A, and we're going to have a B. So we're going to have A plus B, right? And then for the Z bar, we're going to have Z bar, and let's put it over 2. And then we're going to have A, and now we're going to have minus B over I. And 1 over I is just minus I, so that's the same as, let's write it like this, A plus B over 2, and then Z bar of A. And this guy becomes now just plus IB, right? Over 2. And then we see that this guy is this guy complex conjugate, right? So if we define A to be equal to A minus IB over 2, then A complex conjugate is A plus IB over 2, right? So then we can write this thing as Z A plus Z bar a complex conjugate, yeah? Which means that we can write our equation like this. The equation of a line can be written like this for some complex number A itself, yeah? Cool. So we have this nice way to represent the line, which we will use later. Okay, so let's jump back into trying to see what happens to lines or circles as we transform it with this mapping 1 over z. So we were somewhat through the case when we had a circle. So if we have a circle and it's given by the set of z such that mod z minus a squared is equal to r squared, right? That's the general equation of the circle. So we know that if mod a equals mod r, then it's going through 0, and then it's actually transformed into a line. That's what we've seen before. A line, right? And so we're going to have to consider, or we're going to consider the case when this is not actually true, to see what is more general. So we consider mod A is not equal to R itself. So the circle is not going through 0, right? So this is 0, this is A, and we no longer have the radius is going through 0. Something else is happening. Okay, so how are we going to do this? Well, we just expand out what the circle means exactly as we did before. So the equation of the circle can be written as z minus a complex conjugate, z minus a equals r squared, and then we expand that out. We're going to have mod z squared, we're going to have a minus this thing times this thing, and we're going to have a minus a times z bar, which is this guy times this guy, and then we're going to have plus mod a squared, and that's equal to r squared. Now we put the a squared on the other side, so we have this thing, and we're going to have r squared minus a squared like this, right? So last time this thing was 0, so we got something simplification, which isn't going to happen here. So this is not 0, and we are going to divide by mod z squared on both sides. So we're going to have 1 minus a. This is wrong, of course. This is like this, and this is like this. Yeah, we're dividing through by mod z squared. So we're going to simplify this, because what is mod z squared? It is z times mod z. Start again. It's z times z conjugate. So we're going to cancel the z's here. We're going to cancel the z conjugates here, and what we have is therefore 1 minus a over z conjugate minus a over z is equal to this thing. Right? Now, this thing we write as 1 a bar, and this is the same as having I of z complex conjugate, right? Because I is just 1 over z, right? And then this is the same as minus a I of z, and then this thing here is r squared minus a squared times I of z squared. Yeah? Cool. So, so what I said previously, I should have not said at that point. I'm going to say it now. If r squared minus a squared is equal to 0, then what we have here is exactly the equation of a line for the image of z under I. Yeah? So the image of z under I is, I'll start again. the image of the circle under I is exactly forming a line from this equation. That's where we were before. Yeah? But from exactly the same thing, we can see that we can mess around with this and actually get something like a circle, because this was the general equation of the circle, and you can see it's looking a lot like this already, right? It's looking a lot like this already. So what are we going to do? We are going to divide by r squared minus a squared throughout everything. So then this implies that 1 over r squared minus a squared minus a r squared minus a squared, this thing, and minus a over r squared minus a squared. This guy, oops, put it up. Right, and then this thing on the right-hand side is just I of z squared, right? So it's looking more and more like this equation here, right? So when I erase the board, maybe see if I can put everything on the same board. Maybe that's easier. Let's give that a go. Okay, let's see if I can do this on one board. Now, every time I try and do it on one board, it just looks terrible. All right, we're just going to erase. So what we had was, we had 1 over r squared minus a squared minus a over r squared minus a squared times I of z, and then minus a bar over r squared minus a squared times I of z bar. Right, and then this is equal to I of z squared. This is where we were. Right? Cool. And we want to turn this into something like the equation of a circle, because that's what we expect it to be. So we're going to put these guys on the other side, right? So then we're going to have I of z mod squared plus a over r squared minus a squared, z plus a bar of r squared minus a squared, I of z bar, right? And put these on the other side, and then this will be equal to 1 over r squared minus a squared. Yeah, and then let's kind of complete the square to get this expression. So what will do that for us? So what if we do this? What if we have I of z, and let's do minus, well, plus, I was going to do minus, but let's just do plus a over r squared. So if we multiply that out, is that going to work? Let's try this. So when I'm running a squared, I mean mod a squared throughout. So. Specify that. Okay, so let's see if that does the right thing. So when we multiply this and this, then we don't get what we want. So I need to have this and then like this, right? So then if I multiply these guys, I get this and I get this. So that is what I want. So what I'm going to do is I'm going to do this. Yeah. And then that thing is indeed the same thing as minus mod A squared. Yeah? Cool. So we have this thing is the kind of completing the square that'll give us these terms. It'll give us this extra term of this thing multiplied by itself, right? So we have this thing, okay? But what we actually need is to recover these guys. Change color. So recover these guys. So we have from that thing that this is actually equal to mod of z plus a bar of r squared minus mod a squared. And then we are going to subtract mod a squared r squared minus mod a squared. Yeah? That thing is equal to that thing. Yeah? And that thing itself is equal to this thing. R squared minus mod a squared. Like this. Yeah? Okay, so we're almost there. So we put the stuff on the other side, so we're going to have and on the other side, we're going to have, let's make the common denominator. So let's write the top as r squared minus mod a squared. And then, plus mod a squared. So that's a nice cancellation over this thing. Like this. Yeah? Which just turns out to be this, r squared over r squared minus mod a squared. And what we've just written down is the equation of a circle, right? It's the equation of a circle, which is centered around minus a conjugate over r squared minus mod a squared, right? And whose radius is given by this thing. Yeah? Okay, let's see if we believe this. Let's see if we believe that this makes sense. So, if, for example, we have a huge circle, right? A huge circle, but A is just some number, right? So suppose A is here, but we take the radius to be huge, right? What would expect this inversion map to do to that circle? Right? Suppose we have a circle which is like going out like this. We'd expect this inversion map to do what to that circle? Send it to a small circle, right? Yeah. It's still got to be a circle, but expect it to be quite a small circle. Yeah? And then let's take a look. So A is of order 1, whatever. It's much, much smaller than R. We're letting R go to infinity. And then this thing on the right-hand side is indeed going to be very small. It's a small radius because we have a power of 4 of R here, the power 2 of R here. Yeah? And indeed, the center is going down to 0 as well. Yeah? So this is indeed sending this huge circle to some sort of little circle, whatever. Yeah? The bigger circle, bigger radius we take, the smaller radius the inverted circle is going to be sent to. Yeah? Yeah? As we've seen before, if we have a circle whose radius goes through the origin, then this thing turns into a line, right? Which is kind of equivalent to having a circle of radius infinity in this expression here. Yeah? So this thing seems like the right thing, and this has shown that with this inversion map, we are sending a circle either to a line or a circle. Yeah? Just following from the algebra. Okay, so final case to check is when we have a line. So suppose we have a line. And we've now learned that we can think of a line, or we can describe a line as A complex conjugate Z plus A Z complex conjugate is equal to some constant like this. Yeah, that's what we've learned. Cool. So we have cases to consider. Suppose C is not equal to 0. What would you expect this thing to be? I mean, it's got to be a circle or line, but which would you expect it to be? And what does the inversion map do? Suppose we have a line. So we have a line, right? We act on this with the inversion map, right? So it's got to be, if the theorem is true, it's sent to a circle or line. Which do you expect is most likely, given what we've learned? Right, so the inversion map is going to send 0 to infinity, right? And anything which stays away from 0, then it's not being sent near infinity, right? So this line here is not going to get that big. I mean, the image of this can't possibly get that big because we are always missing 0 by something, yeah? Yeah. So if the image was the line, then the line goes off to infinity, yeah? We can go as close to infinity as we like with the line, yeah? So it would be impossible for the inversion map to send this line to another line, yeah? Because we can see the inversion map is not getting close enough to 0 to, it has to go through 0 to actually be sent to infinity, yeah? So we'd expect this line, which is the same as when C is not equal to 0, to be sent to a circle, yeah? On the other hand, if it's a line going through 0, then indeed the image will contain infinity, right? So it should be a line as well. Yeah. So it's kind of analogous to the case of a circle. If a circle went through 0, then it turned into a line. Otherwise, it's a circle. If a line goes through 0, then it's a line. Otherwise, it's a circle. Oh, that's what we expect. That's what we're gonna see. Hopefully, that's gonna come out in the algebra. Yeah. Cool. So if C is actually equal to 0, then we just have A bar Z plus A Z bar is equal to 0. Let's divide everything by mod Z squared, right? So then that's the same as A bar over mod Z squared plus this over mod Z squared equals 0. And then we do the same thing as before. And then we have A, and then we're going to have over Z bar plus A over Z is equal to 0. And that's the same as A times the inversion map complex conjugate plus A times the inversion map like this. And what we have is an equation of a line going through 0 again. Yeah? So in that case, it's pretty easy. Yeah? All right, so now suppose it's not equal to 0. So then we have this. And then when we do this, we get this. Yeah? Which gives us this, which gives us this, like this. Let's divide through by C, right? So let's just rewrite like this. Yeah? And then you can see what's happening. It's the same kind of thing as before. So we put stuff on the other side. Like this. And minus this over this. And plus A over C. Oops, not plus, minus. And that thing is equal to 0. And then we're going to complete the square again to actually get the equation. So what would we expect it to be? Let's try this. Let's do I of Z, and let's try this. A over C like this. If we do this, do we get what we want? We do not. So we're going to do this, and then we're going to do this like this. And then we get this, this, and we get this, this. Yeah, so this thing gives us the first three terms, but we get this extra term like this, right? From this times this, right? So this thing is equal to 0. So then we can rewrite this as like this. Cool. All right. And if we've got this right, then as the line gets closer and closer to 0, then this thing should tend closer and closer to a circle with very large radius, right? And indeed, that's true, because getting closer to 0 means C goes to 0, which means our radius does indeed blow up. Yeah. So our radius blows up, and our center of our circle blows up as well. So this is indeed doing what we expect it to do. Cool. So that proves the result. So Mobius transforms send circles to circles and lines to circles and lines, where we only get a line as the output if the circle or the line goes through 0. Well, if the inversion, start again. So we've shown that the inversion sends circles and lines to circles and lines, and we only get a line if the circle or line goes through 0. But in the general Mobius case, then the 0 has a role which is taken by a different number, because look, we have m of z equals az plus b over cz plus d, right? So as we mentioned before, the thing that gets sent to infinity is the thing that makes the bottom equal to 0, which would be minus d over c. So minus d over c is R0. So if we have a line or circle that goes through minus d over c, then it's a line, otherwise it's a circle. Yeah? Cool. So that is one of the initial remarkable properties of Mobius transforms. Okay, so some more things to tell you about Mobius transforms. So m of z, cool, we're always going to write it like this: az plus b over cz plus d. Okay, so it turns out that we can represent a Mobius transform with a matrix. So I mean, it's obvious we can represent it with 4 complex numbers because it's defined by 4 complex numbers. But the point about this is that composition obeys the laws of matrix multiplication. So if we have, let's call this one M1, and let's call these coefficients A1, B1, C1, and D1. And let's take another matrix, M2, which has got coefficients A2Z plus B2 over C2Z plus D2. Then, if we compose them, M2 of M1 of Z is a Mobius transform itself, and is represented by the matrix given by A2, B2, C2, D2 matrix multiplied by A1, B1, C1, D1. Where matrix multiplication is exactly matrix multiplication in a normal sense. Yeah? And that's kind of a surprising property because these things are very different than mappings from R2 to R2, which is, this is a property which is true for real matrices, 2x2 matrices, when you have mappings from R2 to R2, and you've all seen that. But these are complex 2x2 matrices, and matrix multiplication preserves the representation when we compose two Mobius transforms. So this is just a computation. This is going to be one of your homework questions. You're going to write this out and check for yourself if it's actually true. Yeah? And as a consequence, if we have that the determinant of the matrix, where the determinant is exactly the same thing, which is AD minus BC, is a non-zero complex number, then the Mobius transform is invertible. Okay, which is just a composition of this thing, just a consequence of this composition law. It's just easy to see. So let's see when this is false. Let's see what examples of Mobius transforms actually don't have this property. So suppose the determinant of A, B, C, D is equal to 0, i.e., I guess I could have just written down the equation. AD is equal to BC, right? And so let's look at this Mobius transform. So if we go AZ plus BD over CZ plus CZ plus D. From this relation here, we can see that this is equivalent to A over B, dividing both sides by B, is the same as C over D. Right? So this line is equivalent to that. So let us factor out of B from the top. So then we're going to have A over BZ plus 1, like this. And then let us factor A D from the bottom. So then we're going to have C over D of Z plus 1, like this, right? And AD is equal to CD, right? So this thing is exactly equal to this thing. Yeah? So these things cancel and we just get B over D. Yeah? So in the case where AD equals BC, then our Mobius transform sends everything just to these numbers, to this particular number B over D. Yeah? So it's a very boring Mobius transform. It sends everything, the entire complex plane, to just one number. Yeah? Cool. So we either have a very interesting Mobius transform that preserves lines and circles and maps the entire extended complex plane bijectively onto itself, or we have a very boring one, right? So we just ignore the boring ones because they don't do anything. They just send everything to a point. So we generally consider always assume that this is not the case, that determinant of the matrix is non-zero So, of A, B, C, D is not equal to 0. And often we normalize by this thing because, as you can see, the representation is not unique. So, and note that M of Z written as AZ plus B over CZ plus D, it's not a unique representation. We could just multiply top and bottom by any complex number, right? So a common thing to do is to divide by the determinant of this matrix so that we have therefore a unique representation, right? So that's sometimes what you see. Okay, so that is all cool properties about these guys. There are yet more cool properties. And to do that, I have to introduce something called cross ratio, which is kind of an intricate thing. Okay, cross ratio. So this thing has its origin in projective geometry, and it has a very specific there is background about these things and projective geometry that clarifies it in a way that I'm not going to. I'm just going to use it as a kind of a tool, and it seems a bit complicated, but you'll see how useful it is. Okay, so given 4 complex numbers, let's call them Z, Z1, Z2, and Z3. We're going to form this thing which we call the cross ratio of these 4 complex numbers. So this is a comma, and it's given by this: Z minus Z1 over Z minus Z3, Z2 minus Z3 over Z2 minus Z1. Okay, this is a complex number, right? And if we think about Z1, Z2, Z3 as being fixed, and then Z as being a variable, we can think about this as being a mapping created out of the Z1, Z2, Z3, right? And in fact, a Mobius transform, yeah? So, I mean, sometimes you see notation like this: Z1, Z2, Z3. That's Alphonse notation, okay? So, notice that Z going to Z, Z1, Z2, Z3, I should put this as a definition here. This thing is a Mobius transform. Right? Because what is this? This is just some complex number, and then Z minus another complex number divided by Z minus another complex number. It's exactly of the form of a Mobius transform, like this, yeah? See what I mean? Yeah? Give me a thumbs up. Okay, cool. So this is a Mobius transform, and it has particular properties. So if we plug in various things, we get them sent to 0, 1, and infinity. So let's see what happens. Let's actually call this T, just to save notation. So call it T. So let's see. If we put T of Z1, if we put Z1 into this, then we're going to have on the top here Z1 minus Z1, and this is non-zero on the bottom, and so is this stuff, so it's just going to equal 0. So Z1 gets sent to 0. Yeah? Let's do T of Z2. If we put Z2 into this thing, if we put Z2 into this thing, we're going to have Z2 minus Z1. So let's see if I can just, this is Z2 like this. So we have Z2 minus Z1, which gets cancelled with this thing, and then this thing gets cancelled with this thing, so this ends up just being 1. Yeah? This thing is just 1. Cool. Now, if we put 3 into this thing, trying to save space here. If we put 3 into this thing, let's see what happens. Well, on the bottom here, we're going to have 0, right? On the top, it's non-zero, so we're assuming our Z1, Z2, Z3 are always pairwise disjoint, otherwise we get a boring map, right? And then we're going to get 0 on the bottom, something non-zero, and these things are just some number, so we actually get infinity. Right? So then this Z of t3 is equal to infinity. Yeah? Everybody happy? Yeah? So this cross ratio thing is a mapping that sends Z1, Z2, or let's say that better. The cross ratio is something from which if we consider the first thing, the Z, as the variable, we can think of it as a Mobius transform that sets Z1 to 0, Z2 to 1, and Z3 to infinity. And that's going to be very useful for us, as we're about to see, because that's going to give us the possibility to explicitly describe any Mobius transform if we know that it sends 3 particular points to 3 other particular points. So one of the classic kind of questions you encounter is construct or give a Mobius transform that does this, that sends this to this, and this to this, and this to this. And as a last resort, what you can do is say, okay, well, I see it sends this point to that point, and this point to that point, and this point to that point. So I'm going to explicitly use the formulas I'm about to explain to you to get the Mobius transform. And that's absolutely a brutal thing to do, and that's really calculation heavy. So I would not advise you to do that unless you have absolutely no idea how to do anything better. But that will do it. That will give you the answer. So if you have lots of time left in the exam and there's just one question you can't answer and you can't think how else to do it, and it's a Mobius transform type question, then you could always do that. But there's nearly always a much better way to do it using symmetry properties, which will come as a consequence of this cross ratio stuff I'm about to explain. Well, I think there's actually always a better way to do it. Suppose T is a Mobius transform where it sends, actually let's make a better sentence. And Z1, Z2, and Z3 are 3 pairwise distinct points. Then let Wi be T of Zi, and let W be T of Z for any Z. Then the following is true. That when we take this cross ratio of Z, Z1, Z2, Z3, it is the same as T of W. Oops. It's the same as W, which is T of Z, W1, W2, W3. Okay? And why is this useful? Well, because this thing here is an explicit Mobius transform, and so is this one. So if you know your Z1, Z2, Z3, and you know your W1, W2, W3, then you have these explicit Mobius transforms, right? So this W is this T of Z, by definition, right? So that gives you an explicit formula for what T of Z is that you can solve by solving for T of Z. Okay? So that is what I mean by giving you an explicit formula. So that's why this is useful. Well, that's one of the reasons this is useful. The second main reason is that this gives us an excellent way to define symmetry in a more general way, symmetry across circles as well as symmetry across lines. But that's afterwards. Okay, so firstly we need to prove this. Okay, proof. All right, so let's define S of Z to be this guy. And we're going to find T of W to be this guy. Right? And we've already learned that S of Z1 was 0, S of Z2 was 1, and S of Z3 was infinity. Right? And we've learned that same thing is true except for the Wi here. So this W is 0, T of W2 is 1, and T of W3 is infinity, right? So these guys send these three distinct points to the same three distinct points, right? So if we have Z1, Z2, and Z3, and let's say we have, let's change color, W1, say W2 and W3, right? They are being sent to 0, 1, and infinity. Like, wrong way around. So Z1 to 0, W1 to 0, Z2 to 1, and Z3 to infinity, right? And W1 to 0, W2 to 1, W3 to infinity, like this. Yeah? So we can invert these guys because these are non-trivial guys. They're not sending everything to one particular value, right? By definition, right? So these are both invertible Mobius transforms. They're not the trivial ones sending everything to a constant. So then we can invert it. So for example, we could take Z1 going to 0, and then with the inversion of this guy here, which is T, send it to W1. Start again. I said that wrong, and I've used the letter twice because T is our transform here. So let's not call that T, let's call that R. Let's call that R, because T is our original guy. Okay, so this is our guy S, and this is our guy R. So we can take Z1, send it to 0 with S, and then send it to W1 with R inverse. Yeah? As you see from the picture. We can take Z2, send it to 1 with S, and then send it to W2 with R inverse. And we can take Z3, send it to infinity with S, and send it to W3 with R inverse. Yeah? Cool. So that means that if we create S of, oops, the other way around, if we create R inverse composed with S, of Zi, then it's equal to Wi for I equals 1, 2, 3. Yeah? Yeah? Cool. And that's the same stuff that our mapping T is, right? Because that's how T is defined, sending Zi to Wi. Yeah? Yeah? Cool. All right, so that means that if we, let's write this underneath it as well, and T of Zi equals Wi, which is the same as saying that T inverse, again, it's a non-trivial mapping because it's sending distinct things to distinct things, T is equal to Zi. Yeah? For I equals 1, 2, 3. Yeah? So then we can compose t to the minus 1 with this thing. So t to the minus 1 of r to the minus 1 of s of Zi is therefore equal to Zi for I equals 1, 2, 3. Yeah? And I claim that that means that this thing, which is the composition of 3 Mobius transforms, actually has to be the identity. Because what is it doing? It is fixing 3 points, and I'm about to show you that that's impossible for a Mobius transform unless it's just constant. So the Mobius map Z goes to t to the minus 1, r to the minus 1, s of z fixes 3 points. Claim. This implies it's just the identity map. T to the minus 1 of r to the minus 1 of s this is just equal to z for all z. Okay, let's see if I can squeeze the claim in on the same page. Okay, so generally, suppose we have that AZ plus B over CZ plus D is equal to this. Let's try and see how many solutions of this we have. Well, we just multiply it through, right? So we're going to have AZ plus B is equal to CZ squared plus DZ, right? And we're looking at a nice quadratic equation. So then we have that CZ squared plus D minus AZ minus B is equal to 0, right? And it has at most 2 solutions unless it becomes a degenerate quadratic, which is just a line, right? And in order to become a line which has, well, a line has infinitely many solutions, but in order to become a degenerate quadratic, and therefore just a line, we need that this thing here, the C is equal to 0. Yeah? So if C is not 0, then it's definitely a quadratic, and then it has at most 2 solutions. Okay, so if more than 2 solutions, or of then C is equal to 0, right? And therefore, the equation is dz minus az is equal to b, okay, which is the same as z of d minus a is equal to b. Yeah? So, in what way can we have more than 2 solutions of this equation? How is that possible? If d equals a, we do indeed have everything satisfies. No, that's not true either, because it would need the right-hand side to be equal to 0. So if D equals A and B is 0, then we would have lots of solutions of this, right? So, but if D is not equal to, so let's do case by case. So if D minus A is not equal to 0, then, and B is not equal to 0, then there's just one solution, and we just write it explicitly down, right? Right? So that's impossible, yeah? So we need some of this stuff to be equal to 0. So if, are we okay for time? If D minus A is equal to 0 and B is non-zero, then this equation is impossible, yeah? D equals 0, then there's no way that this equation has any solutions unless B is actually equal to 0, yeah? And implies B equals 0, but then we get A is equal to D, and then our entire Mobius transform just turns into just, so this thing, we're going to have B is 0 and C is 0, so the Mobius transform M of Z just becomes AZ over D, which is just equal to Z. It just becomes the identity mapping. Yeah? So, the conclusion of this is that if we have more than two points that are fixed by a Mobius transform, which is the same as having more than two solutions to this equation, yeah, that can only happen if we have the identity mapping. Yeah, can only happen with the identity mapping. Yeah, cool. And so therefore, that claim is true because we have that this thing fixes 3 distinct points. Yeah, fixes 3 distinct points. So this thing is indeed equal to this thing for all Z. So it's absolutely an identity. Yeah, which means that we can unwrap this. Let's see if we put this on the same board. That R of -1 of S of Z is equal to T of Z. So I have like my backup watch, and it looks to me like I'm at 43 minutes past. Is that right? Or have I overrun? Okay, so I'm actually quite okay. Yeah, no, that is right. It's misreading on my watch. All right, cool. So we are here, which is good. And then let us rewrite that as S of Z is equal to R of T of Z, and then that's exactly what we want. Oh, I've erased the statement of the theorem. So the statement of the theorem was this, right? That this is W, W1, W2, W3, right? And this guy here, so rewriting the statement of the theorem, so rewriting the statement of the theorem, what is this thing? So this is our mapping defined by S. So that's S of Z. And this is our mapping defined by R. So that's R of W. That's the same thing as this, right? This statement is the same as this statement, but W is just equal to S of Z, R of T of Z, which is exactly what we have here. Yeah? Cool. All right. So we have established this result. We've established the result. And all we needed to do was just notice that when we drew this picture, we could create this mapping R to the -1 composed with S that sent Zi to Wi, the same as T did. So we consider the composition of T to the -1 with this thing, which fixes 3 points. And if it fixes 3 points by this little calculation, the only way that can happen with 3 pairwise distinct points is if it's the identity, which is exactly the statement. So the proof actually isn't that hard. Yeah? Proof actually isn't that hard. Cool. So that is cross ratios. And I'm going to give you Actually, maybe give you first a warm-up of what we mean by symmetry with respect to a line and then with respect to a circle. Okay, so we say Z1 and Z2 are symmetrical. I'm going to write sim dot for symmetrical from now on because I'm going to use the word symmetrical over and over. With respect to line L, if and only if Zy minus this, Z2 minus this for all Z belonging to the line. So if we have a line, wherever it is in space, we have 2 points, Z1 and then Z2, then having them being symmetrical with respect to the line, I mean, there's many equivalent definitions you can give, but this one's perfectly good. So for any Z, consider the distance from Z to Z1 and Z to Z2. If those distances are the same for every possible choice of Z along the line, then Z1 and Z2 are symmetrical with respect to the line. Yeah? That's a nice way to define symmetry. Yeah? Okay, so that is with respect to a line. Now, with respect to a circle, it's a bit harder. So consider a circle. So let's try and define symmetry with respect to a circle of radius 1 around 0. So suppose C is the boundary of the ball of radius 1 around 0. What do we mean by symmetry with respect to this ball? So if this is the origin here, so by symmetry we mean that we're going to reflect it through the boundary of the ball. So symmetry with respect to a line is the same as saying that when we reflect through the line we get the other point, right? Yeah. But we don't have a line anymore. We have a circle we're reflecting to. So what properties will we want from a reflection through the surface of a circle? Well, if we reflect a point to the surface of a circle, say this point, we'd expect it still to be on this line, right? That would be a natural thing to expect. Yeah. So it should be somewhere on this line. So Z bar should be somewhere on this line. So sorry, Z star, which is a symmetric point, should be somewhere here. Yeah? And we'd also expect that if it's actually right here on the circle itself, then it's not going to change at all. Yeah? So here nothing should happen. When we reflect a point through the surface of the ball and it's on the surface of the ball, nothing will happen. Just like if we reflect a point actually on the line, through the line, nothing happens. Yeah? That's another property we'd expect. But we'd also expect that as we get closer and closer to 0, then the reflection gets sent further and further to infinity. Yeah? That's what we expect. Yeah? Cool. So we're just going to try and come up with a map that does that. So let Z be x plus iy. Right? And I'm going to work in coordinates and I'm going to turn it into complex notation afterwards. So just thinking in terms of coordinates, then let's do something like this. So we say Z star, which is x star plus y star, is symmetric with respect to C, if and only if. So let's generate something that does this. So what we want is Z star is going to be in the same direction as Z, right? But let's write it in coordinates instead. First of all, if and only if. So I'm going to write in coordinates like this. So we want x star, y star. We want it to be in the same direction as xy, right? But let's divide it by the absolute value of the vector xy squared. Because if we do this, so this is a definition, then if mod xy equal 1, in other words, we live on the circle, then nothing happens, right? Then nothing happens. Yeah? And as xy tends to 0, then x star, y star tends to infinity. Yeah, and it's on the same line, right? It's on the same, so let's say it's on the same ray from 0 to infinity as xy itself. Yeah, so let's replace this with xy. Right. So this thing indeed is the right notion of reflecting through the surface of the ball of radius 1. Are you happy with that? Yeah? Cool. So, in complex notation, so then we're going to write z star is going to be equal to z over mod z squared, like this, right? Which is the same as z over z complex conjugate z. So 1 over complex conjugate is actually doing exactly the thing that we want. Yeah? Cool. All right. Now, let us think about reflecting through something of radius r. So suppose that we have C is the ball of radius r around 0. Okay, and it's the same kind of game. We expect it to be, let's just adapt this diagram. We expect it to be on the same ray, right? Yeah. And we expect it, as we get closer to 0, it gets towards infinity. But the main difference is that the surface now is here, and this is where we expect nothing to happen. Yeah? We expect nothing to happen if we reflect something that's actually on the surface of the ball of radius r. Yeah? Cool. So how would we adapt this formula right here? Well, if we define, let me make a sentence. X star, y star, to be something similar to this, except that we're going to multiply it by r squared, so like this. Yeah. Then all these properties of remaining on the same ray, 0 being 10 to infinity, are true. And when it happens that xy is on the ball of radius r, then this thing on the bottom is r squared, so we end up not changing it at all. Yeah. So, and if x comma y belongs to C, then x star, y star is just equal to xy. Yeah. So that thing does the thing that we want. Yeah. Okay. Now, in the most general situation, we are now going to do this around a ball of radius a. Okay. And we still expect similar stuff, right? We expect as we go towards A, we get towards infinity, we want to remain on the same ray, we want nothing to happen if we're on the boundary of the ball. Yeah? Cool. So this is how we're going to adapt it. So we're going to define x star, y star, like this. And now we're considering how close we are to A, so we're going to do this. We're going to go xy minus a over xy minus a squared. We're going to have to multiply by this r squared thing here, right? And then we're going to have to add a to everything to put it back on the ray centered at a, right? Okay, so let's break this down. So if we have, choose another color, some point like this, yeah, then we take xy minus a, right, this vector here. So let me put this in brackets. We take xy minus a, yeah, and then we divide by the length of this vector squared, so that the vector is going to be sent very long towards infinity in the same direction as xy tends towards a, yeah. We have this normalization r squared. In case we are on the surface of the ball, let me write that better. It's not much better. We have this normalization here. But this thing is just a vector whose base is 0. So we need to put it back onto A in order to get it along this ray here that I've drawn. Yeah? You see what I mean? So this more complicated expression, this guy is indeed the thing that we want. So we can just check. So it's definitely on the ray, right? So this is going in the same direction, right? Because this is the direction. So it's the same direction. And then we add A. So it's definitely on this line, on this ray. Yeah? It's definitely true. Yeah? It's definitely the case that as xy tends towards A, this thing's going towards infinity. That's definitely true as well. Yeah? And we need to check that if we're on the surface, then we just get back the point itself. So if x comma y is on the circle, then what happens to this thing? Well, on the bottom, we're going to have exactly r squared. Yeah? So that r squared will cancel with this r squared. So then this will give us x minus y minus a plus a. So then we are back up where we are, right? X star, y star. Let me write a little bit of this is x comma y minus a plus a, which is equal to x comma y. So back on, it's not changing anything if we're on the boundary of this circle. Yeah? After we're in the boundary of the ball, therefore the circle. Cool. So this more complex expression gives us exactly what we want. And now let's write it in complex notation. So in complex notation, we're going to have z bar is going to be equal to mod z squared. Sorry, this is r squared here, the radius of this thing. And then this thing is z minus a. And now we're thinking of a as being not a point in R2, but a complex number. Sorry for the reuse of a. And then over z minus a squared. And then that is going to be r squared. And then just z minus a complex conjugate like this. Plus a. I missed the plus a. And then this is r squared over, so small down here. Okay. Z minus a complex conjugate plus a. That thing is giving us our notion of symmetry through the circle. And the claim is that with this notion of symmetry, we have that any 2 points and any line or circle where the 2 points are symmetrical with respect to that line or circle, once we map those characters with, characters in the sense of a story, when we map those characters in the story into the new world with a Mobius transform, we're going to have another 2 points and either a line or a circle, and the symmetry relation will be preserved. Yeah? So whatever you have, if you have a circle and you have these 2 points that have this symmetry relation, and then you map it with the Mobius transform, maybe you get a line, and let's say this is Z1 and this is Z2, and this is circle, and then this is T of this. But now you'll have that T of Z1 and T of Z2 will satisfy symmetry like this. Okay? Or this could be the image of this is a circle, and then T of Z1 and T of Z2 will satisfy symmetry with respect to that circle. Yeah? And same as if you have a line and then you map it, same thing happens. And that thing is the most useful property in figuring out what Mobius transforms have to be. So we know that they're angle-preserving mappings, but this is a lot stronger. This is saying that all symmetry relations that you see are preserved. And I mean, it's an extraordinary strong property, which is why this kind of feels like a weird branch of geometry. There's this weird space, this weird world where there's different notion of symmetry, where you can transform this with these fairly non-trivial looking mappings. I mean, they do quite strange things, but nevertheless, all symmetries are preserved. here's a test question for you. Suppose we have just mappings from R2 to R2. Yeah? Let's consider a very special class of those mappings. Let's just consider linear mappings, therefore things representable by 2x2 matrices. Is it the case that for those mappings, symmetries are preserved in the sense that I've just described? Oops. I should say pairs were distinct rather than disjoint. Never mind. Then Z and Z bar are symmetrical with respect to Mobius transform with respect to C, if and only if the following is true, that Z, Z1, Z2, Z3, this cross ratio is the same as C star of complex conjugate. Okay, so while you were thinking, I put the statement up, we'll talk about it in a second, but first answer my question. Is it true that if we have linear mappings, they preserve symmetries in the sense that we just talked about? I mean, linear mappings are nice, right? These are the nicest not completely trivial mappings from R2 to R2 we could come up with, pretty much, right? Although, maybe not quite the nicest, but yeah. So is it the case that linear mappings will preserve symmetry in the sense that we think? Okay, so that will be another homework question then. So think about that. Think about if it's true or not. And if it is true, give me a proof. And if it's not true, give me a counterexample. Yeah? Cool. All right, so this is what we're going to prove next time. That with this notion of symmetry, this is equivalent to taking our cross ratio created from these 3 points and an arbitrary Z, the cross ratio created from Z and then these 3 points and Z bar and 3 points, where these are any 3 points on whatever we have, so long as they're all distinct. Right? And then we should have that we have symmetry with respect to the circle or the line or whatever we have. So if this is, for example, Z, then symmetry might be Z star. Then we have the symmetry is true if and only if this happens. And a posteriori, given what I've just told you, that we're later going to find out that Mobius transforms preserve symmetries, this shouldn't be a complete surprise, because we know that this thing is itself a Mobius transform when we think about Z1, Z2, Z3 being fixed, right? And there's a Mobius transform that sends Z1, Z2, Z3 all onto 0, 1, and infinity, which is the real line. Yeah? So this Mobius transform is sending whatever we have, whatever C is, line or circle, onto the real line. Yeah? Yeah? So what this statement is saying is that once we take whatever object we have, line or circle, we take a Mobius transform to map it onto the real line, then this guy here, let's say, is this guy could be here, right? And say it's right here. And then this guy has to be here. Because when we have this relation, that's exactly the same as saying that Z star, or well, let me say that better. It's exactly the same as saying that this number is symmetrical with respect to this complex number across the real line, right? Because W and W star, W and W star are symmetric with respect to R if and only if W is equal to W, if and only if W is equal to W star conjugate, right? This is W and this is W star, right? Because to get from one to the other, all we do is put a minus sign in front of the imaginary part, right? So W conjugate will send us exactly here. So again, W star conjugate will give us exactly this. Yeah? So symmetry with respect to the real line is exactly having this relation, right? So these guys here, this complex number here, which is the image under the Mobius transform, and this guy, which is the image under the Mobius transform of T star, they this equation here is exactly saying that they are symmetrical with respect to the real line. Yeah? Symmetrical with respect to the real line. So this is a way of defining symmetry by mapping everything, mapping whatever object you have onto the real line and saying, okay, we have symmetrical if they are symmetrical with respect to the real line. Yeah? And it's going to turn out, I'm going to show you that this gives us exactly the notion of symmetry that we discussed previously. Yeah? And it's a kind of a, yeah, it's a kind of, it's a taste of this more general phenomena that Mobius transforms preserve symmetries in this sense. All right, so that's it for today. Have a great day, and I will see you all on Thursday. Bye-bye, people.